So continuing with our idea about what derivatives tell us, we move to a different feature of the graph. All right, so we were previously looking at increasing and decreasing of the function, and that's an important thing. We use the first derivative to tell us that. Now we're going to look at something called concavity, and we'll see how it leads to the idea of inflection points. Okay, so if we're talking about concavity here, let's look at what that means. Basically, that's talking about how the function is bent. So in this first example, this would be f concave up. All right, it's shaped upward. It's open up. Okay, so this would be concave up. Now, let's take a look at the next one, which would be f concave down. So this one is faced down, so it would be concave down. So that's how we determine concave up or concave down just from looking at the function itself. So we do want to link this back up to derivatives though. So let's take a look at something. Okay, so in this first picture here, the concave up one, notice that if I look at tangent lines, so I'm going to draw in some tangent lines here. Okay, so notice what's happening there. As I move from left to right, all right, so when I'm here, over here, at the left, I see that this tangent line has a very negative slope. So it's a very big negative number, let's say negative 100. Okay? And as I move along the curve, and I'm going to move left to right, look at what happens. Then the tangent line is still negative, but not as negative. Then finally, when it gets to the bottom there, it gets to 0, and then it's a little positive, and then it's very positive. So notice, throughout that whole time, the derivative, the slope of the tangent line, the first derivative was increasing. All right? Because it went from very negative to 0 to very positive. So it was always increasing. And so we have the function concave up, meaning that the first derivative is increasing. But now think about derivatives. If we just look at this first derivative as a function and we say it's increasing, that means its derivative should be positive, because the derivative of a function tells us increasing or decreasing, tells us increasing when it's positive and decreasing when it's negative. So since f prime is increasing, its derivative f double prime would have to be positive. So now we've linked it to the second derivative. So the second derivative positive means concave up for the original function. Similarly, if we look at the concave down example, let's move through the function from left to right. Very positive slope, somewhat positive slope, 0 slope, somewhat negative slope, very negative slope. So over this whole time, f prime was decreasing. And if a function is decreasing its derivative, so now f double prime is negative. So there's what we've done. We've connected the second derivative positive to the function being concave up. And we've connected the second derivative negative to the function being concave down. This will allow us to take the second derivative and have it tell us about the original function's concavity, so how it's bent. All right, so how does that work? Well, here's your test for concavity. Let f be a function whose second derivative exists on an open interval I. F double prime greater than 0. In other words, the second derivative positive means the graph of f is concave up. The second derivative of f negative means the graph of f is concave down. All right, we do have an issue that if the second derivative is 0, then it's neither concave up nor concave down. We'll have to see what that means when we look to some examples. But it shouldn't be too surprising, because imagine a straight line. Okay, a straight line has a constant slope, so it has a constant first derivative. But then if you took the second derivative, it would be 0, saying that the line here is not curved concave up nor concave down. It's flat, so it has 0 concavity there. So now let's take a look at an example and see what we would do with this. All right, find the open intervals on which the graph is concave up and concave down. All right, concave up and concave down, so that means we're going to have to look at the second derivative. So what we're going to do, we're going to need to take the first derivative to get to the second derivative. So 3x squared minus 6x and then 0. All right, and then we'll have to take the second derivative, 6x minus 6, which is 6 times x minus 1. All right, so now what we're going to do is we're going to look for any zeros of the second derivative or places where the second derivative might be undefined, just like we did with critical points in looking for the first derivative being 0 or first derivative being undefined. So let's say, when is the second derivative equal to 0? And when is the second derivative, that should be the second derivative of x. And when is the second derivative undefined? Well, when's it equal to 0? X equals 1. When's it undefined? It's not. All right, so then I would make a chart again, just like I did, but this time it's for the second derivative. All right, so now I'm going to put any discontinuities or any of these points that I just found over there. So I'm going to put 1 there. Then I'm going to go into my second derivative, and I'm going to start plugging in numbers from each region. So we could plug in 0 over here. All right, so if I plug in 0, I'm going to get 0. I'm going to get a negative. And if I plug in, say, 2, I'm going to get a positive. So that tells me now second derivative being negative tells me the function is concave down. And then it tells me that over here where it's positive, it tells me f is concave up. All right, so I can answer my problem now. So I'm going to give intervals where it's concave up and intervals where it's concave down. It's concave up on 1 infinity, and it's concave down on negative infinity to 1. And there we have it. Note we did it just like we did with the first derivative, except we're using the second derivative And now it's telling us something different. It's not telling us increasing or decreasing of the original function. It's telling us concave down or concave up of the original function.